Hello good people, I would like to explore the E1 reaction mechanism. E stands for elimination and the number 1 tells us that the rate determining step, the slowest step, involves only one molecule. In this particular case, that would be the substrate. Now before I even look at the reaction, we need to get some nomenclature out of the way. The carbon that is attached to the leaving group is referred to as the alpha carbon. The carbons next to it are referred to as beta carbons. Consequently, a hydrogen that is attached to a beta carbon, for example this fellow here, is referred to as a beta hydrogen. Alright, so what happens? As the name suggests, the leaving group leaves and a nucleophile comes in. However, unlike in a substitution reaction, the nucleophile does not replace the leaving group. It does not substitute the leaving group. Instead, it is attracted to one of the beta hydrogens. And when all is said and done, it leaves with one of the beta hydrogens, and the major product is an alkene of some sort. Alright, let's have a look at a more specific example. Here is my substrate, 2-chloro-2-methylbutane. The first thing I'm going to do is label the carbons. So this one is the alpha carbon, these ones are beta carbons, and I'm also going to number the carbons. 1, 2, 3, and 4. What is the first thing that happens? Well, it's an E1 reaction mechanism. That means that the rate determining step is the formation of the carbocation. So the electrons between the carbon and the chlorine will end up with the chlorine. As a result, we'll get the carbocation and also the chloride anion. Once again, I'm going to label the carbons so that we can keep track of what is going on. And I'm also going to number them again. And now I'm going to bring in the nucleophile. I have chosen water in this particular case. Now the nucleophile has a choice of 2 beta hydrogens. It can be attracted to this beta hydrogen here, so the hydrogen on carbon number 3, or it can be attracted to a beta hydrogen on carbon number 1. I will explore both scenarios in turn. So let's see what happens if the water is attracted to the beta carbon on carbon number 3, so the blue hydrogen. Pardon me, if it is attracted to the beta hydrogen on carbon number 3, not the beta carbon. Alright, so it will be attracted to the blue hydrogen. The electrons between carbon number 3 and the hydrogen will end up between carbon 3 and 2, forming a double bond. And our product would be 2-methyl-2-butene. This is also known as a Zaitsev product. More on that in a moment. Please note that the water, the nucleophile, has ended up with the blue beta hydrogen. Alright, what is the other scenario? The other scenario is that these electrons will be attracted to the orange beta hydrogen. If that happens, the electrons between carbon 1 and the hydrogen will end up between carbon 1 and carbon 2, forming a double bond. And we would end up with 2-methyl-1-butene. Please note that the beta hydrogen, that the water has now ended up with the orange beta hydrogen, and the double bond is formed between carbon 1 and 2. Okay, so now let's compare the Hofmann product and the Zaitsev product. So firstly, let's look at the Zaitsev product. In the Zaitsev product, the double bond has been formed between carbon number 2 and 3. This alkene is more substituted. In other words, the carbons that are part of the double bond are bonded to more non-hydrogen things. So if we look carefully, we can see that the carbons of the double bond are attached to 3 non-hydrogen things. If we now look at the Hofmann product, the carbons of the double bond are attached to only 2 non-hydrogen things. That means that the Zaitsev product, this one over here, is the more substituted one. And recall that the more substituted alkene is more stable. Therefore, the reaction mechanism will tend or will favor the more stable product. In this particular case, that is the more substituted alkene, and we refer to that as the Zaitsev product. Now, In most cases, elimination reactions will go towards the Zaitsev product. However, there are scenarios where the Hofmann product will be favored. That is determined largely by the choice of base you decide to use. In this particular case, I have used a relatively small base, water, and a relatively small base will favor a Zaitsev product. If I had used a more bulky base, such as tert-butanol, the Hofmann product would have been favored. That is all for now, and I will see you on the flip side.